Hello.
Yeah,
Can
I
you
can
hear
hear now. I can hear now. All right. Okay, earlier I couldn't hear anything. Okay. Yeah, so can somebody answer my question? Remember my question? So imagine it is a letter to letter renaming. That is, there is a map from A to B, and that is extended as a morphism. That's called letter to letter renaming.
Yeah, then just replace every letter on the automata with its image.
Yes,
It's yeah, it's yeah.
exactly. So you just replace, you go to every transition of the automata, erase the letter A and write the corresponding letter of B. Yeah. So it's easy. So images under morphism is easy for non-deterministic automata. So you see that there is a trade-off between complementation and images under morphism. Trade-off. So if if complementation is easy, then images under morphism will be difficult. And if images under morphism is difficult, then complementation will be easy. Another, so for instance, you already saw it on that for non-deterministic automata, NFA. Images under morphism is easy, but complementation is different. Has anybody seen alternating finite state automata? Alternating automata. Anybody familiar with this alternating finite automata?
Yeah. So you
Yes.
have for all, and there exist on the
Yeah,
node,
exactly.
and you have okay. Yes.
So basically, non-deterministic automata, for every letter, you are branching existentially. You are saying that you go to one of these states, but if you could go to all states, it will be called universal branching. Yeah, I mean, anyway, I can't go into the definition of alternative finite automata. That's not our this thing. But for alternating automata, complementation is easy, but images under morphism is difficult. It's exactly the opposite of non-deterministic finite automata. And for monoids, you already saw that complementation is easy, so images under morphism should be difficult. In fact, you look at these two operations, one of them should be exponential in the size of the original accepting mechanism. Okay, so for monoid, complementation is easy, therefore images under morphism has to be exponential. And so therefore, images under when the monoid which we construct will be in principle be exponential in the size of the monoid M. Okay, so that's something you can't avoid. So how do you construct this the monoid recognizing H of L? Anybody did that?
Maybe 2 power m, and uh, you map take an element in
Mm-hmm.
B star, and uh, take the pre-image with respect to H,
Yeah.
and consider all the elements that the in the monoid that go from these elements to the monoid.
Yes. So the observation is that if M is a monoid, if I mean monoid, then 2 power m with product operation x dot y is equal to xy such that x is in x and y is in y. That's a product operation on subsets of 2 power n is a monoid. It's a monoid. And uh, and so you define a morphism G from B star to 2 power m by mapping W to all H of h of, no, we don't have a, so let's imagine M, there is a morphism from A star to M, which is mu L, the canonical morphism of L. Okay. So then W maps to mu L of W prime, where h of W prime is equal to W, where W prime is in S star. Okay. So with this morphism, it will recognize. Okay, so that you can verify that. I'm not going to verify it now. Now that was the exercise. And morphism under inverse images, I already told you in the last class, it's done easily. Okay. Now let me go to today's topic, which is rational sets. Okay, so far we have been talking about recognizability and recognizability by finite monoids. So our general the whole idea about recognizability, I mean the the whole idea is that you have acceptance or definability by finite structures. Yeah, that the languages which you are going to study are subsets of an infinite structure, infinite set, and you are actually exploring what can you finitely present, what can you finitely define, and so on, define using finite objects and so on. So we already studied one such notion, which is recognizability, which is definability by morphisms into finite structures. And the next kind of there is another kind of finite definability, which is called rational sets. Okay, or what is this rational sets? So you say that i have I have a monoid M. Okay, it could be a star, it could be a free monoid, it could be some arbitrary monoid, and I define rational subsets of M to be one empty set is rational because it is finitely presentable. Then if A is in M, A is in M, then that is also rational. Or let's say A. Okay. Then if X and Y are rational, then X union Y is also rational. Okay. So you will also write it as X plus Y. You can also write it as X plus Y. Then if X and Y are rational, then X dot Y. So what is this X dot Y? You take all products of the form small x times small y, where X belongs to capital X and Y belongs to capital Y, is rational. And finally, if X is rational, then X plus, which is X plus X square plus X cube, this infinite series, and X star, which is X power 0 plus X power 1. So X power 0 is the identity of the monoid. Okay, are also rational. Okay, so what have I done? I have written some. So if I miss some arbitrary monoid, I have written some subsets of M to be rational, empty set, then singleton sets, and if X and Y are rational, then rational subsets are closed under union. So from 2 and 3, you get that all finite subsets of M are rational, because in singleton sets are rational, and These are closed under unions, not arbitrary unions, finite unions. So therefore, from 2 and 3, you get that all finite subsets are rational. Then if x and y are rational, x dot y is also rational. And if x is rational, x plus and x star are rational. Now, this looks suspicious. This looks like something from regular expressions, and that's not accidental. The terminology rational came much later. Initially, it was introduced by Kleene, uh, and yeah. So these are the rational subsets. So let's make some observations. All all subsets of a finite monoid are rational. Okay, all finite subsets of the monoid are rational. Then um, rational subsets of um, let's say Z plus. How do they look like? Rational subsets of Z plus. How do they look like?
Ultimately periodic sets.
Yes, they are ultimately periodic sets. It's not. I mean, it's not that obvious, but I mean, you can think for 10 minutes and then you will realize that it is ultimately periodic sets. What is ultimately periodic sets, or you can actually write it in this form. So um, are ultimately periodic sets. Okay. So what is ultimately periodic? X subset of n is ultimately periodic if for all there is n0 in n such that and p in p, I mean, I should write it as n0 and p, n0 comma p in n such that for all n greater than n0, uh, n0 is n is in x if and only if n plus p is in x. Okay, so you will put a bound, and after that bound, everything has to be periodic. Okay, and uh, rational subsets of, I I mean, actually, it could be just z also. Okay, z power k are semi-linear sets. Okay, semi-linear sets. Now, what are semi-linear sets? Um, Anybody know the definition of semi-linear sets?
Yeah, so sets of form A plus B n, where A and B are in Z bar K, and um, n is in natural numbers, I guess. Yes.
Yeah. Yeah. So semi-linear sets, a linear set um, is actually given by
It's 11 o'clock.
uv uh, where uv are finite subsets of z or k is, so you can see them as vectors, k dimensional vectors. It's a set of all vectors u0 plus k1 uh, v1 plus k2 v2 plus etc plus k and vn, where u0 is in v, u v0 v1 up to vn are in v, and k1 to kn are in natural numbers. Okay, so that is a linear set. And semi-linear set is a finite union of linear set. You might wonder why they are important. They are important because they pop up in many places of computer science. For one, they are precisely the sets definable by first order logic over Z bar K. If I could write a formula using only addition and zero and greater than, less than, and so on. Yeah. So my vocabulary is zero, greater than, less than, equal to the relations, and then addition operation. I can write x plus y equal to something. So for instance, I could write that there exists um, or z bar greater than uh, 0, 15, 30, and so on. Yeah. So let's imagine x bar, y bar, z bar are three-dimensional vectors. So I could actually write such equations, and such equations are nothing but formulas. You have to imagine. Yeah, they are just simple formulas which are universally quantified. That's all. I mean, sorry, they are just simple formulas uh, which has these as free variables. Then such equations, the solutions of such equations are nothing but, or such formulas are nothing but semi-linear sets. Yeah. Uh, that's one place where they could turn up. Another place where they turn up is in the uh, what is that? Chomsky Schutzenberger's theorem. Oh no, sorry, Parik's theorem, which says that if you look at the alphabetic vectors of, or they are also called Parik vectors of words in a regular language or a context-free language, they are nothing but semi-linear sets. Yeah. So what does that mean? So if I have a language L and I have the, let's say, alpha of w, which is the alphabetic vector. So for instance, if a, b, c, then this corresponds to the vector 2, 1, 1. Yeah, if I imagine the first one corresponds to a, second one corresponds to b, third one corresponds to c. So if for every word, I'll get a vector. Now, if I have a context-free language L, then its alphabetic vector, first of all, context-free language for context, the alphabetic vectors of context-free languages and regular languages are the same. Why? Because if you give me any context-free grammar, I could actually convert it to a right linear or left linear grammar. I can just move up all the uh, um, variables to the right, and then that becomes a regular language. Yeah, so that's why if you look at the paric vectors of or the alphabetic vectors of context-free languages and regular languages, they are exactly the same. And so Parik's theorem says that the alphabetic vectors of context-free grammar, context-free language, is a semilinear set. Okay, and they turn up in lots of other places also, but yeah. So this is one place where it is another place where semilinear sets turn up, which is rational subsets that per k are semilinear sets. Anyway, you can read about it in elsewhere, but anyway, they're not directly connected to our study. Uh, okay. Okay, so that's enough observation. So now, do they coincide? Do recognizability and rationality, how do they compare? So there is one theorem which you learned. What is that theorem? Kleene theorem says that over the free monoid, they coincide. Yeah. So if you give me a language over L over A star, which is a finite alphabet, finite free monoids. I should say finite free monoids. Over finite free monoids. Yeah, finite free monoids. Anybody has any doubt about what does it mean to say finite free monoids? Ah,
We can even say that it would be like a finitely generated free monoid, right?
yes, I should say finitely generated. Actually, that is right. I should have just said finitely generated free monoid. Okay, because a finite free monoid is nonsensical because after all, the monoid is not finite. Yeah, even if, yeah, so it should be finitely generated free monoids. They coincide. And this is a theorem which you learned, yeah, in your theory of computation. Basically, I can construct an automata for the recognizable set, and then I can turn it into a regular expression, and that's what is, uh, one direction. Yeah, every language which is recognizable is rational. That is one direction. Actually, it's a difficult direction there, where you have to construct the automata and turn it into a regular expression. The other direction is much simpler, which is that you have a regular expression and then you have to convert it into an automata, where you go via induction. Yeah. Okay. So you have seen this theorem, and it's a non-trivial fact because you will see that immediately that it only holds for. I mean, it holds only for finitely generated free monoids. Over arbitrary monoids, they are two different notions. Okay, so that's what we are going to see today. Okay, they coincide. Okay, and they over, I mean, it's pretty simple to come up with a counter example where over arbitrary monoids they don't coincide. Over arbitrary monoids, they don't. These two notions don't coincide. One simple example is that you 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 consider a no, I mean a monoid which is not finitely generated. For instance, uh, you consider right zero semigroup which contains infinitely many right zeros, yeah, or omega many right zeros, and then yeah, if you consider the entire set, that is recognizable because you could take the trivial semigroup, trivial monoid, and you could map every element to that trivial monoid. So the entire set is recognizable. That is anyway true because you give me any monoid, the entire monoid is recognizable because I could just map it to the trivial monoid, and that is recognizable. But it is not rational because uh, we will see that it is not rational because here you will see that rational subsets of M are actually subsets of a finitely generated submonoid of M. Okay, maybe that's our, we can start with that proposition. So let's write the proposition. Rational subsets of a monoid M is or are or maybe I should are subsets maybe I should use in singleton sentence. Um, Tens a rational subset of a monoid M is a finite, is a subset of a finitely generated submonoid of M. Okay, a rational subset of a monoid M is a subset of a finitely generated submonoid of M. What does that mean? That means that if I have a monoid M and I have a subset X which is rational, then actually I can find a submonoid which is finitely generated, and this submonoid and X is contained in this submonoid. Okay, maybe I mean maybe there is a better way to write it, but I think the idea is clear. A rational subset of monoid M is a subset of a finitely generated submonoid. Okay, how do we prove this? We can prove it by the induction on the structure of the rational subset. Okay, so if proof, so we go by we go by the structure of the rational subsets. So if my rational subset is empty set, then it is actually so here it is the finitely generated submonoid. So then it is actually the submonoid of empty set itself because it is finitely generated. If it is just A, then it is actually generated by, it is the submonoid of A star. So then if it is X and Y, how do we do this? Let's say X plus Y, how do we do this? What is the finitely generated submonoid which contains x plus y?
The union of the elements that generate X and the elements that generate Y.
Yeah. So let's
Isn't
call
it?
it, yeah. So let's call this let's call it um, fx and fy. Okay. Star, where x is subset of fx star and y is subset of fy star. So if x and y are if x and y are rational, then by induction hypothesis, I know that they are generated by they are subsets of finitely generated submonoids of M. So I'm going to call fx and fy the generators of that respective submonoids. So then x plus y is actually fx plus fy whole star is a submonoid of fx plus fy whole star. Yeah. Is it clear? Hello?
Yeah.
Okay. And if it is x dot y, then again fx plus fy star. And if it is x star, then if it is just fx star. Okay. So basically, what you from this what you get to know is that rational subsets are subsets of finitely generated submonoids. So from this, immediately you see that if you have if you have a infinitely generated monoid, for instance, an infinite right zero semicolon, then that monoid itself uh, cannot be a rational subset. Okay, all right. So all right. Now let me give one concrete example of our finitely generated, but it's not just our infinitely generated monoids, but even our finitely generated monoids. These notions diverge. It's just that they don't have to be free. Okay, but maybe um, I'm going to write a proposition. That's probably the most important uh, proposition for rational subsets. Okay, let h from m to n be a morphism. Then if x is a rational, so m and n are arbitrary monoids. If x is a rational subset of m, then h of m is a rational subset of n. So what does this proposition means? Rational subsets are preserved under morphisms. Okay. So if I have a rational subset are preserved under morphisms. Now the second, there is a converse also. if further, if H is, what's the time now? If H is surjective, then if R or X, I should say Y. If Y is rational subset of N, then there is an R, there is an R subset of M, that is, there is an R. There is a then there is a rational subset R of M such that H of R equal to Y. Okay, so what is this proposition means? So first part of this proposition says that rational subsets are preserved in a morphism. Second part of this proposition says that you can't expect rational subsets to be preserved under inverse morphisms. That doesn't hold. But what holds is this. If I have a rational subset in N, then there is a rational subset R in M such that H of R is actually this Y. Okay. All right. So let's prove this. So this is one.
Sir, so is this like saying that H inverse of Y might not be rational, but there exists like a sub-rational subset of H inverse of Y?
Yes, that's what it means. That's what it means. H inverse of Y is it may not be rational, but there is some subset of that which is rational, and that will map to Y. That's what it says.
Oh.
Okay. So let's first prove the first part. Rational subsets are preserved in the morphisms. So how are we going to prove that? So we are going to prove that by saying that it's not both proofs are very, I mean, they're not very difficult. Just kind of observing certain facts. Okay, so how are we going to do this? So first, let's prove. Let's prove this way. Let F be the subsets of M, that is, whose image under H is rational. Okay. So what I'm going to do is that I'm going to collect all those subsets of M whose image in N will be rational. So certainly the empty set belongs to F because H of empty set is equal to empty set, and empty set is a rational in N. Second, individual element A is in F. A is in F. Why? Because H of A is rational. Because H of A is a singleton element in A. So it is rational. If X in F and Y in F, then X plus Y is in F. Why? Because why is it the case? If X is in F, that means that H of X is rational. Y is in F, it means H of Y is rational. So H of X plus Y is actually H of X union H of Y. is rational. Yeah, because we already know that x is in F, therefore h of x is rational. H of y is in F, therefore h of y is rational. H of x and h of y are rational in N, so therefore h of x union h of y is also rational in N. And therefore I get that h of x plus y is in F. Okay. Then if x is in F and y is in F, then x dot y is in F. Why? Because x is h of x is is rational, h of y is rational, and h of x dot y is h of x dot h of y. Because h is a morphism. Okay, and this is rational. Okay, so let's look at what is h of x dot y. H of x dot y is all h of small x dot small y, where x is in capital X and y is in capital Y. And that is nothing but h of x, h of small x times h of small y for every x in capital X and small y in capital Y. And this is nothing but h of capital X times h of capital Y. Okay, and finally, if x is in F and then x star is in F. And what is the reason? H of x is rational and h of x star is h of x whole star, which is rational. Okay, I hope it is clear. You just have to think a little bit. It's not h of x star is all finite. So x star, one way to think about x star is all finite products in from elements from x, and that is nothing but all finite products of h of x. Okay, so therefore you see that therefore rational subsets of M are subset of F, because we started by saying that I am collecting all those subsets F whose images under H is rational, and I show that rational subsets of M are subsets of F. There could be other sets whose image is rational, but certainly rational subsets of F M are subset of F, and that proves the first part of the proposition, which is that images of rational subset is the rational subset. Okay. Any questions? Any question? Okay. So then let's go to the next part. Let me call it A. This is A. Now let's prove the next part, B. Again, this idea is the same. So what do we have to prove? We have to prove that I have M, I have N, and I have to show that for every rational subset, I can find a set R here whose H of R is rational. This is Y. How do I do that? Any suggestions?
Can we proceed the same way by induction on the structure of rational sets?
Exactly. We are going to proceed the same way. So let's imagine, first of all, structure of rational subsets of n. Okay. So empty set. So here I'm going to put subset of M. Okay. So here I'm going to put rational set of n. So for every rational set of n, I have to find a corresponding subset of M that is rational. Okay. So if it is empty set, if I'm taking empty set here, then I can take empty set here. Yeah. If I'm taking empty set here, I can take empty set here. If I'm taking a singleton set A here, what can I take here? What can I take?
We can just pick one element from H inverse A, so any one element.
Exactly. So we'll just pick some B where B, H of B is equal to A, just one element. That is where we just have to be careful, because I mean, if we just take H inverse of A, it could be an infinite set, and we may not be able to, that may not be rational. So we just have to pick one element each. Okay. And if it is X plus Y, then let's call this map, let's call this correspondence mu. Then you put mu of X union mu of Y. Or yeah. So by induction, we have constructed for every set here, I have picked a subset here, and so for X, I have taken a subset of M, which is mu of X, and for Y, I have taken a subset of M, which is mu of Y, and for X plus Y, I just take a mu X union mu Y, mu of Y, and that will map to X plus Y. Yeah. So image of mu of X union mu of Y, H of mu of X union mu of Y will be nothing but X plus Y. X dot Y, what will be X dot Y? What will be X dot Y? Are you following what I'm doing? So for X, imagine I have picked mu of X, and Y I have picked mu of Y, and I look at their product. Okay. And their product will map, H of that product will be nothing but X dot Y. Okay. And X star, it will be mu of X star. Okay. And so in each case, what I'm picking on the right side are rational subsets. And that is how I can ensure that for every rational set on the right hand side, I can find a rational set on the left hand side that will map to it. Okay, so you have to think a bit more. I don't know if all of you are clear with that, but it's not complicated. Okay, so anyway, let's come back to the proposition. What does it say? It says that for every rational set, images under rational sets are rational sets, and for every rational set, I can find a pre-image that is I can find I can find a subset on the left hand side that will map to it. Okay, subset that is rational. And from here, we can actually prove that. I'm going to prove that even on finitely generated monoids, rationality and recognizability need not coincide. That's what we are going to prove. Okay, so I'm going to take A star, which is all finite words over which contains A, and BC star. Okay, all words over the alphabet B and C, BC. And I'm going to take the product A star cross BC whole star. Okay, so it's a product monoid, and in this monoid, I'm going to show that there are recognizable sets. There are rational sets that are not recognizable in this. I mean, actually, what we are going to show is that rational sets are not closed under uh, intersection. So that will show that it's yeah. So if I look at A1 is 1. I'm going to denote by 1. I'm going to denote empty word of either monoid. So if I look at A1 star dot A no, I'm going to put 1 is 1B dot AC whole star. This will give me a word A power n, B power m, C power n, such that mn greater than 0. Yeah. So if I look at the set 1B whole star dot AC whole star, that will give me A power n, B power m, C power n. Yeah, the number of A's and C's has to be the same. If I look at 1C, if I look at A B whole star dot 1C whole star, what will be that language? What will be that language? Anybody? Yeah.
It will be like A to the N, B to the N, C to the M.
B to the m. So is that m n greater than or equal to 0? So let me call it x or C and D. C and this is D. C intersection D is nothing but A power n, B power n, C power n, such that n is greater than or equal to 0. Okay. Okay. So first of all, C and D are both rational subsets of this product monoid. Yeah. Because this is a finite, this is a element whose star, and then this is an element whose star, and then their product. So both C and D are rational, but their intersection is this set: A power n, B power n, C power n. Okay. Now both C and D are rational. Now, but C intersection D is not rational. Why it is not rational? Because if C intersection D is rational, then B power n, C power n is rational. Okay. Why? Can you tell me why? If C and C intersection D is rational, then B power n, C power n, the set B power n, C power n greater than or equal to 0 is rational. Why?
Projection is a homomorphism.
Yes, exactly. Uh, because of the theorem which we just proved, which is that the rational sets are preserved under morphisms, images under morphism. So I can actually take the projection morphism from this monoid to just this monoid, okay, which maps every element here to just its second component, which is called the projection morphism. So if C intersection D is rational, then B power n, C power n greater than or equal to 0 will be rational. But we know that this is B power n, C power n is not rational over the free monoid over AB. Yeah, we know that over this is a free monoid, and we know by Kleini's theorem that rational subsets and recognizable subsets coincide, and we know that B power n, C power n is not recognizable. So therefore, we know that B power n, C power n is rational, but it is not. Okay. So therefore, we know that C intersection D is not rational. And hence, we get from this observation or this example that rational sets are not closed under intersection. Okay, and they are not closed under intersection. Also, they are not closed under complementation, because if they are closed under complementation, then because they are closed under union, they are closed under intersection, they will be closed under, if they are closed under complementation, they will be closed under intersection. So therefore, rational subsets are not closed under intersection or complementation. Okay. So we see that rational subsets are over even for finitely generated monoids. They differ from recognizable sets. Okay, and I don't have much time today, so this is what I wanted to cover. So we see that rationality, the nomenclature rational comes from the fact that they can be written as there is another formulation of rational sets in terms of power series. We won't go into that, and the nomenclature rational comes from there. Rational power series. Yeah. There are a couple of theorems in your textbook where it is shown that a couple of theorems are proved. One is that I don't think I will go and prove that because we have more important things to do. So there are a couple of theorems. One theorem is that you see that rational subsets are not closed in intersection. What about intersection of a rational subset and recognizable set? So it turns out that intersection of a rational subset and a recognizable subset is again rational. It's more like yeah. Anyway, let's not go into that. So intersection of a rational set and a recognizable set is again rational. There is a proof in your book. for that. It's not complicated. It's I would encourage you to read that. Then another theorem is that um, if your monoid M is finitely generated, I can actually write it here, theorem. The following are equivalent. One, M is finitely generated. So this theorem comes from this context, the following context. You know that Clini's theorem says that over finitely generated free monoids, rational subsets and recognizable subsets coincide. And we just saw that over arbitrary monoids they don't hold. Now, what can you say about um, how much can you save that theorem? And that is what this says. So if M is finitely generated, that is one. Every recognizable subset of M is rational. M is a rational subset of M. Okay. And yeah, this is McKnight's theorem. Okay. This proof of this is also there in your book. Yeah. So I would I will encourage you to read these two theorems. And in the next class, we will start with Green's relations. Any questions?
Did you correct the quiz papers?
Yeah, actually, I forgot about that. That's what happened. Actually, I corrected this one. I just remembered it today morning. I will upload it in couple of hours.
Okay.
Yeah. Any other questions? All right. If there is no question, see you next week. I don't have. Let me see if there are some exercises. So with that, we have come to the end of 4th chapter. Yeah, the exercises at the end of chapter 4 are good, but yeah, but I don't find anything which I should give you as an exercise. But you're welcome to try it out. All right then. See you next week.
Thank you, sir.
Yeah, bye.